All right, so at long last, round three of Bernoulli effect stuff. Okay, let's go. Hey, so we're talking about the Bernoulli effect. Bernoulli effect will look a situation like this. Let's start off with the equation. What do we notice here? They're all the same height. So when they're talking about the Bernoulli effect, they typically are talking about things that are level. So it means the same height. So what they're really kind of getting at here is that as velocity increases, then pressure will decrease, and that's it. So here's the example that they use. There's a flow going this way, and then it narrows here. It narrows, so that means the speed goes up. Since the speed goes up, that means the pressure goes down, the pressure decreases. Now you can see this because it's not pushing up on this column as well as it is pushing up over here. The atmosphere is winning more on the middle because it's pressing down and it's getting lower. Nice. Now there's one major application, and that is airplane wings. Ta-da! Hey, so what you'll notice is this top half of the wing is longer than the bottom half, which is shorter. Since the top half is longer, but the air will meet up at each beginning and the end, that means that at the top it is longer, and that means that it is going faster. It's going faster, and the bottom means that it's going slower. So, since the top is going faster, what happens to the pressure? That means there is less pressure on the top, and that means there is more pressure on the bottom. So what does that mean? There's more pressure here. Let's just say there's 100 pascals of pressure here. Let's say that there's less pressure here. Let's say there's 50 pascals. Doesn't matter what it is. Now, if we take the airplane wing and rotate it, so it looks, like a normal airplane wing, beautiful. Would you agree that there's an area here? Gorgeous. Let's say that the area is equal to 10 meters squared, just for funsies. Well, what that means is that you have pascals. Remember, pressure is equal to force divided by area. If you have 10 square meters and you have 50 pascals on that, that means that there is 500 newtons of pressure that's pressing downwards on this wing. Now, the same is happening here. There's 100 pascals, so there's going to be 1,000 newtons pressing up because there's more pressure. Now, you could subtract these first, yeah, and then do this. That's totally fine and dandy, but you will notice that there is a net force. The net force is going to be pressing up, and that helps the airplanes take off. Remember, airplanes taking off is the hard part. Landing them is easy. Okay. So what we're going to do, let's do some practice with this. Water flowing at 4 meters per second passes through a venturi tube as shown. This is another name for this theorem, or the principle, Venturi principle, or Bernoulli principle. Doesn't matter. It's the same thing. If h equals 6, what's the velocity of the tube in the constriction? So this guy is 6. We want to figure out what's the speed going to be. All right, we're going to start off with the Bernoulli equation. We're going to leave off everything that deals with height because we have this nice level playing field here. That's what they like these days. All right, P plus 1/2 rho V2 squared 2, 1, and 1. Okay, well, let's think about this. You have a difference in pressure, so we have to have a difference in velocity. Let's worry about the difference in pressure first. The difference in pressure is causing this 6 centimeters. Well, we can figure out what the difference in pressure is. So we have a fancy formula. Hopefully you remember it. P is equal to rho GH. Okay, rho is 1,000 because it's water, times 9.8 times H, which is 0.06, because we're in centimeters. So that means the difference in pressure is going to be 588 pascals. All right, so it doesn't matter how you do it. This guy here, we'll call this P1, is going to be more than P2, and we just got to put it in either way. So I'm going to keep it simple. I like adding. So P1 is equal to P2 plus 588, and that's going to be adding to, remember this is all together here, so that's going to be 4 1/2 times 1,000 times 4 squared is equal to P2 is just P2. Younger siblings will know the significance, right? Times 1,000 times V squared, and we're solving for V. And you'll notice that we can cross out the P2s because it's just the difference. Could have done the same way with the subtraction. Doesn't matter, it's just moving it around. All right, solving time. V is going to equal 4.14 meters per second. Does that make sense? Yes, it does. It makes sense because it should be more than 4. So it should be going faster through this area because there's less area, just like the good old days. Remember that flow rate stuff? Oh, yeah. All right, let's do another fun example here. They're all kind of the same, but you know. We've got an airplane wing designed so the speed of the air across the top of the wing is 251, where the speed across the bottom is 255. The density of air is this number. What's the lifting force on the wing of that area? Okay, you should pause it, see if you can solve it. I'll catch up to you. Boy, it took you that long, huh? All right, so P1 plus height doesn't matter here, so it's just going to be 1/2 rho v squared is equal to P2 plus 1/2 rho v2 squared. Okie dokie. So what we're looking for is the difference in pressure here, so I'm going to rearrange it just a wee bit. So delta P is going to equal, just move the P1 minus P2. So we're going to have 1/2 rho v2 squared minus 1/2 rho v1 squared. Could have done it the same way with numbers. 1/2 1,000. V2 is going to be 225 squared minus 1/2 1,000, 251 squared. Put it all together. Delta P is going to equal 7983 pascals thereabouts. Nice. Not done yet though. P is equal to F over A. Well, I know 7983 is going to equal F, which is what I'm looking for. Divided by A, the area is 24. Multiply them out, so the lift force here, the force lifting the airplane up, is going to be 192,000 newtons, or kilonewtons if you're into that kind of thing. All right, hey, and that's it for fluids. Hopefully you're noticing that it's all running together. Get it? Get it? All right, make sure you have good times with this stuff. We'll see you later.